Hello, my name is David Williams. I'm one of the developers here at Lucid, and I'd like to show you our new Energize programming system. We've built Energize for programmers. It's designed to work the way that programmers work, and designed to make programming in C and C++ faster and easier. It's faster because Energize's incremental compilation technology means that you only recompile and relink the parts of your program that you change. And that's going to save you a lot of time. It's easier because Energize gives you a complete view of your program and allows you an easy way to navigate around all of its components. All of this is made possible by three technologies where Energize is at the forefront: object-oriented programming, integrated development environments, and advanced user interface design. We're going to see more of those as we move through a demonstration. So let's get started. For the purposes of demonstration, we're going to take a look at a simple C++ program. We're going to find a problem, fix it, and test out our changes. So let's go ahead and find out just how easy to use Energize is. Okay, the first thing to note is that Energize is a very editor-focused system, because most of the work we do as programmers is inside an editor. The editor that we use in Energize is the very popular Emacs editor, and to that we've also added a VI mode. Showing in the editor at the moment is two buffers: the Energize top-level buffer, which lists all of the projects in the system, and in fact one of those projects is here, the dclock project. A project in Energize is a module or a library. You can see that the project buffer lists all of the components of the project. The project was created by simply compiling dclock source files. The compiler transmits its fine-grained understanding of your code to the Energize server, where it's stored in an object-oriented database. This means your program information is always going to be instantaneously available. You'll notice that as I move around the project buffer over the different items in it, that each of these items gets highlighted. That's because they're Energize system objects, and I can click on them and it'll give me a list of operations that I can perform. And this is the basis of the way we move around inside of the system. So for example, a file here can be edited, check for errors, etc. A project has a different set of operations: edit, build, debug. Why don't we go ahead, load up the debugger by saying debug target to have a look at our test program. So we start up the debugger and it's brought up in another editor buffer down the bottom here. Notice also that we've added this little control panel up the top here for the debugger, which gives us quick access to the most common debugger features. So why don't we go ahead and run the test program. So here's our little test program here. As you can see, it's a very simple digital clock. It tells the time, and when we press Q, the program terminates. When we press Q, the program terminates. Okay, we seem to have a problem. So that's what we're going to work on. We're going to find out why Q doesn't work. So let's start off by stopping the program, and we'll get a backtrace. And here's our backtrace. Now, at first glance, the backtrace that you get in the debugger is like you would get out of any other old debugger. But it's different. You see, as I move around, you'll see that there's, again, a number of objects in the system, which get highlighted as I move the cursor over them. For example, argv here, which is the arguments to the program itself, is listed here by this variable. So I can click on it, it's an object, so I get a list of operations that I can perform on it. Let's say print star. Energize knows what the object is, and so prints out the invocation string to the program in a sensible fashion. The frames themselves are objects. Let's go ahead and look at run, because that's sort of like the top loop of the deface class, and we're going to focus on that for a little while. So let's go ahead and we can get a list of things that we can perform on it, and one of those is show frame. Show frame is going to take me to the source, so let's do that. And the editor gets sent a message to load up the deface.cc file with the cursor positioned over the deface run function. So this is the way source looks inside of the Energize system. And this is not just a display-only tool. This is the same editor that we've been using for everything else. So we can go ahead and edit our source directly. Okay, a couple of points to note about the source. First of all, there's all these little icons in the system indicating more information. This one here, as you might have guessed, is a pointer indicating where the program counter is. So we're stopped inside of the read function, inside of the run function. And if we check against the backtrace, yeah, that's correct. Run is calling read. Great. Second thing here is these little green icons. Now what do they indicate? Well, what they mean is that all of this function is what we call a language element, as is the function above. Well, a language element in the Energize system is any part of your program. Function, a class, hash define, a variable. All of the elements of the language, hence the term language element. Let's have a look at what's actually going on inside of this function. This is the main loop of the digital clock, so it's an important place to start. While not done, read an event, handle the event, and then tick over some counter. Okay, it looks like done is some kind of flag indicating when to terminate. So we're reading the event, okay, when we hit the keyboard it beeps, so we must be reading all right, but we're not handling it correctly. Instead of exiting when I press Q, the program, just beeps. So we're going to focus on handle in a moment, but as it's a member function of dface, let's try and find out a little bit more. Because it's an object-oriented world, let's find out a little bit more about the dface class. And we can do that very simply. You've already seen how. We can click on this language element and it gives us a list of operations that we can perform. One of those is browse class of language element. And if we browse the class of this language element, that's going to bring up information about the dface class. So let's go ahead and do that. And this brings up what we call the language element browser. And the language element browser is a textual tool that displays information about language elements. So here we have information about the class dface. We see that it's where it's defined, the base class that it's derived from, all of the data members and function members defined for this class. And of course, each one of the items displayed here in the language element browser is an object itself, so we can click on it, and again, it gives us a list of operations that we can perform. Okay. We came into the language element browser by clicking on an object and saying bring up all the information about that object and displaying it in the language element browser. Sometimes we don't have an object in front of us. So to help out that situation, the language element browser has a control panel. So let's have a look at what that does. The control panel is used to name an object, so we can specify a name or a pattern to bring up information about objects in the database. It's like a query tool. So let's change what we're searching for. We'll look for dface : draw star. And so anything that has the name dface : draw star. We'll continue to search in all of the files, and let's just restrict searching to the dclock project. We'll just look for functions. We won't look for classes, macros, variables, or types. So at the moment, we're looking for functions that match that name. That's what the top half of the control panel controls. The bottom half is what we're going to get. At the moment, we're getting very detailed information. So let's turn that off. And we're all set to go. Let's push apply. And you'll see now that we get all of the functions that match this regular expression up here. So you'll see there dface draw : or dface draw, and a number of other permutations of the draw star pattern. Okay, as you can see, all of these are objects, so again, we can click on them. Okay, and we can use that to traverse around the system. It's the basis of how we get around. The language element browser is very useful for getting textual information. And the really great thing is that, like most of the other components in the system, the information is displayed inside of an editor buffer. So we can edit it, save it to a file, do all of the things that we do with normal text. We get a nice user interface plus the flexibility of ordinary text. Well, that's the textual view. Sometimes it's good to get a graphical view of what's going on in the system. And we can do that quite simply by, again, clicking on an object and looking at the operations we can perform. One of the things we can do to a member function is graph class of language element. So let's do that, and that's going to bring up the grapher tool displaying a class hierarchy for the dface class. And you can see that dface inherits from the base class interactor. It's a very simple class hierarchy. You'll see that this little 3 suggests that there may be more information in the graph. In fact, what it's saying is that there are 3 other classes derived from the base class interactor. If we want to have a look at those, we click on the 3, we get a menu saying show right nodes. We get a new graph and showing all of the classes derived from the base class interactor. And in fact, we can go ahead and adjust our graph, hiding and showing nodes, to get more or less information. Like the language element browser, the class browser has a control panel. And we can click on that and adjust the information that is displayed in the class tree. Let's say, for example, that we wanted to find out if the horizontal box class implemented its own draw function. That's very simple to do. We just type in draw in the function search slot, say yes, I want to look for functions, and push apply. And we get a new class graph showing all of the draw functions in the classes that implement it. So we can determine very easily and very visually from that horizontal box doesn't implement its own draw function, it inherits it from the base class box. Okay, it's a really simple and powerful tool. Let's just change it so that we're showing all of the member functions for each of these classes. So we make that adjustment, push apply. We'll just hide the panel back down to give us more room. So you can see now all of the member functions defined for each of the classes that we're currently showing. You'll see that a number of these classes have so many functions that they wouldn't fit very well on the screen. So the grapher in fact puts them in a little scrolling area which we can move up and down without taking up too much of the screen. Okay, we came into the grapher to find out a little bit more about the dface class, because we wanted a sort of broader view of what's going on inside our program. Now let's return to handle and focus in on how handle could be affecting our program. And we can do that simply because handle here in the dface definition is an object. We can click on it and we can say, for example, graph calls. And this is going to bring up the call tree browser showing us that handle is called by the run function, as we would remember from the run definition, and in fact calls these other functions. Okay, so this is the call tree browser. And again, we only show the parents and children of the focus of the graph. Again, we have a control panel and we can make adjustments to the graph. Okay, let's return to the source of handle and see if we can find out what might be causing the problem. That again is easy to do. We click on the object, we get a list of operations that we can perform. One of those is edit definition, which is going to load up the editor with the handle source. So now we're back in the editor and we can see here, here's the definition of the handle member function, or the source of the member function. So let's have a look at what's happening. Okay, now remember from run that we've already read the event and we need to handle it. And to terminate the program, we need to set the done flag to true. So let's see what's going on. So we say, okay, switch on the event type, and it's a key event because I'm pressing Q to terminate the program. And remember, we need to set done equal to true to end the program. So okay, if it's a key event and the event length is greater than 0, key string is equal to or equivalent to A. Well, there's the problem, I think. I think that's going to be the problem because that should be a Q. It looks like some kind of a typo. And then that's going to set done equal to true. Yeah, that makes sense. Well, let's go ahead and confirm that. We'll put a breakpoint there, which is very easy to do. We just say set breakpoint, and the system automatically updates the source to indicate the breakpoint with this little stop sign. Also note that the grapher was updated, again showing the stop sign object. Okay, let's go ahead and run our program again, and this time, yes, we want to restart the program, and this time we'll press A and see if that is in fact the terminating key at the moment. Okay, A, and we come in here, we hit our breakpoint. Let's just step through there. And in fact, yes, we're going to set done equal to true. Okay, let's continue that on and let the program terminate. Okay, here's the change where we have to make it. Let's disable that breakpoint and go ahead and make our change. Okay, we've made our change. Now what's happened here? The background highlighting has changed. Okay, what that means is that we've edited that function, so it's now out of date. It needs recompilation. Well, how did that work? Well, it's really pretty simple. The editor really only knows about text and character positions. So it sends a message off to the server saying, hey server, I just edited deface.cc file at character position 2000, say. Well, the server knows a little bit more information about our program. It looks up in its database and it says, well, deface.cc, line 2000. Well, actually what you've done is you've edited the definition of the deface handle object. So that object is now out of date. It needs to be recompiled for the system to be up to date. So the server then sends out a message to all the tools that are currently looking at that particular object saying, hey, you're working with this object and it's just changed, it's out of date. So redisplay that object in such a way that the programmer will know that, that it's changed and needs recompilation. One of those messages comes back to the editor, and the editor is told to redisplay that region of text so that the programmer can see that this function is out of date and needs recompilation. And that's why we get this background shading effect, which, as you can see, is a really good visual clue of the effect of our change. Okay, we've gone around, we've used the browsers to focus in and find the problem, and we've used the debugger to make sure of that. We've made our change, so now we're ready to build a new version of the program and test it out. So let's go ahead, save our change, and recompile. And of course, using Energize, we're going to do an incremental compilation, and all we're going to do is recompile the handle function in the deface.cc file, and then as soon as the compilation of handle is completed, which it seems to have done, we're going to take our changes and link them back into the main program. And the link is very fast because, like compilation, we do an incremental link. And then it will automatically tell the debugger to restart, and it looks, yes, it's already done that. It restarts the debugger with a new executable image all set to go. So let's test out our change. We'll run the program, and now when I press Q, the program stops. Great, our change works. So, couple of things to note there. Notice that when the compile was really fast. We did an incremental compilation, incremental link. That's great. We're going to talk a lot more about incremental compilation in a moment. Then we had a new executable. Now, in an old style environment, we'd have to shut down the debugger and restart the debugger because all of its information is out of date. Well, with our system, that's done for us automatically. The server sends out a message to the debugger saying, hey, your target has changed, reload your symbol table information, reload all your debugger information, reload your breakpoints, and we get a new ready-to-run debugger session that's automatically done for us. We as programmers don't need to worry about managing our tools. The system does it for us. And we get a new program ready to run very quickly. Okay. That's all I wanted to show you in the first part, basically the way we move around the system, how easy it is to use the Energize system, how easy it is to find out all the information we need to know about our program. Now we'd like to focus a little bit more on the incremental compilation technology and see how much that is going to benefit you in your very large programs. To do that, I'm going to do something which C and C++ programmers really don't like to do. I'm going to edit a header file. So let's load up the project buffer and load up a header file. And we'll go down to enumerator type in here. And what we'll do is make a change to this enumerator type AMPM mode. Add an extra field there, and we'll just save that back. Okay, so we've updated the deface.h header file. Now, in an old style environment, that would mean that we'd have to go and recompile all of the files that include deface.h. So let's see who in fact does that. It's quite easy to do. We can just click on the object up here, the deface.h object, say where included, and that's going to show us that deface.h is included by deface.cc and declock.cc, two C++ files. So again, in an old style environment, because of the change we've made, we're going to recompile deface.cc, recompile declock.cc, and then do a full link, dragging in all the libraries again. Okay, let's have a look what Energize is going to do. Now, first of all, AM/PM mode is used by, just a couple of functions, or, 3 or 4, who knows. It's not going to be used by every single function in those two C++ files. So let's find out, in fact, who's using it, because in terms of the language, that's the only thing that needs to be recompiled. So let's click on that, and we can use the language element browser to tell us who's using AM/PM mode. And there we go. We see enumerator type AM/PM mode is used by the class dface. Well, that doesn't have any code associated with it, and it's also used by the dface set function. So there's in fact only one function that is using AM/PM mode. So really, in a perfect world, that's the only file, the only function that we would need to recompile. And that's exactly what Energize is going to do. Just compile that one set function and incrementally compile and incrementally link. So let's go ahead and do that. But before we do, I'm going to bring up the tool status tool. And the tool status tool is the third of the tools that you use in the Energize system. And it basically tells us what's going on in the system. It tells us the status of all of the tools. So as we do the compilation, we can see the progress in the toolstat tool. So let me go ahead and build our target. So we go down to the toolstat tool, and we see first of all the compiler starting, and just to compile the set function in the dface.cc file, and looks like it's just about done doing that. Now the compiler will call the linker, there it goes, and this will link the new set function back into the object file, and then finally our main link linking our changes back into the declock target, and it's all done. Okay, it's really fast, as you can see. Let's talk a little bit about what happened there. First thing is dface.cc. We recompiled dface.cc to recompile that one function set. Let's say there was 10 functions in dface.cc. 9 of them, they don't need to be changed because they don't use AM/PM mode, and it's the only object in the system that has changed. So let's leave them alone. We'll leave them there in the dface.o file. We recompile the set function and produce a very small object file called an object incremental file, dface.oi. We take that object incremental file and then link that back into the dface.o object file. And we end up with a new dface.o, which is incrementally manufactured. It's completely compatible with standard tools, but it was made really fast. That's the incremental compilation part. The next part is when we link, and here we get a really, really big win. Just think about sort of programs that you usually work on. You drag in the C libraries and the C++ libraries and the X libraries, the database libraries, and all of that other stuff. 90% of your program is code that you never wrote and code that doesn't change whilst you're developing it. So we thought at Lucid, well, it's kind of silly to go and get them from all the library directories around the system. You've got them there in the program file. So that's what we use. We reuse the information in the program file, and we take our new object incremental, our incrementally updated set function, and we link that back into the main program, reorganize things, produce a new executable program, which again is completely compatible with standard tools, but was incrementally manufactured. And as you can see, it's really fast. And of course, it automatically loads up the debugger, so we can go ahead, run our new program, and there it is. Well, that's all we have time for now. We've seen how easy Energize is to use. Just click on an object, pull down a menu, and follow the link. Energize is based around tools that you're probably using now, so you'll be up and running in no time. Second, we've seen that Energize is a truly tightly integrated system. All of the tools are kept up to date automatically by the system, so you can focus on your program instead of wasting time managing the tools. Finally, we've seen that Energize's fine-grained understanding of your program means that a small change that you make doesn't mean you have to recompile and relink everything. Programming using an incremental compile and link is just plain fast. Energize is easy to learn, easy to use, and it saves a lot of time. If you've got any questions, then please give us a call. Thanks for watching.